I will talk about 2 problems. I should have enough time. Okay. I had a couple of problems. Okay, we are going to study. Okay. The first one, okay. So here's the first one. Okay. The first one, we're going to try this area, surface area as a surface, which is generated by rotating the curve y equals, okay, for example, cosine half of x, okay, x is between 0 and pi, and this is about the x-axis, okay. I probably use this example to find this, use this example and then to do similar other problems, okay. So find the area of the surface of revolution. Find the area of the surface. Okay. So step 1, you draw the graph. You have to draw the graph, okay, correctly. Okay, x and y. Now, when x equals 0, cosine 0 is 1. So this is a point here. When x is equal to pi, cosine half pi is 0. So this is a cosine curve. Okay. So it's rotated about the x-axis. So you have to draw a 3D picture. Yeah, how do you draw? Just draw like that. Okay. Make it looks like a 3D picture. All right. Next step to set up in formula. So you write down the universal formula. Okay, 2 pi r ds. Don't write down the direct formula. Okay, the specific formula. So what is r? What is ds? You have to clearly state here. Right after that. Okay, you take a point on the curve. Okay, and you draw the radius. That is r. Okay, so r is going to be y, right? If you use the coordinates on that point. Okay, ds, now it depends. If you want to get the integral with respect to x, that is 1 plus dy over dx squared dx. Okay, so that's it. So if you do that, then you have to set y to be cosine half of x. All right, so the area is going to be from 0 to pi, 2 pi cosine half of x, and then you differentiate cosine, so it's going to be negative sign, so negative is gone, so I just sign half of x squared and dx. So that is the integral for the surface area. Okay, now next step. Okay, you have to find a way to integrate. So up to right now, if you already get like 60% of the credits, okay. Okay, you think about how to yes, you think about how to evaluate the integral. What is the best idea right now? Okay, to solve the to evaluate this integral. I use substitution, right? I think we have to use substitution. So let u to be, I'm going to just use half of sine, half of x, okay? Because I want to get 1 plus u squared. So du equals a quarter cosine half of x, right, dx. That's good, okay? So this part will be 4 du. So the integral, okay, when x is 0, that's a 0. When x is pi, that is just equal 1/2, right? U is 1/2. It's 2 pi and the square 1 plus u squared. And the cosine half of x dx is just 4 du. So finally, I get 8 pi from 0 to 1/2 1 plus u squared du. Okay. Then you get a very special integral. Now, if we stop there, and when you stop there, you get 90% of the credits, right? And then you have to look for the formula in the book, table of integrals, right, to evaluate them. Okay. Otherwise, you have to spend more time to use another substitution to evaluate this integral. Right? I'm trying to find the one which is a formula number 21. Okay. So number 21, you can use that. Okay. The entire derivative is going to be half of u, 1 plus u squared, plus half of natural log u plus this. Okay. And evaluate at these two endpoints. Okay. So you have to put all the numbers into this put the 1/2, plug 1/2 for u, and you have to complete the steps. Okay, it's a quarter, 1 plus a quarter, and half. You don't need it to simplify it. Okay, and then minus 0. I think when everything's 0, this is 0. 0, natural log of 1 is 0, so I don't have another term. Okay. So that's it. Okay. Now for the same problem, I cannot evaluate the integral. Okay, I want to set up. Okay, it's cosine half of x. Okay, this time I'm not going to. Its a notation is about about the y-axis. Okay, so the graph looks like that. Okay, okay. That's the second question. Set up an integral for the area of the surface of the erosion. Okay. Right. So take an arbitrary point. Again, you have to learn this, otherwise you're confused. And you don't know what's going on. Then sometimes you put the variable y there, sometimes the x variable. And if you do not use this idea, it's a 50-50 chance you'll get a wrong integral. Okay, I will see that. All right, so now, you write down the formula. This is a universal formula, 2 pi r ds. Okay, and you draw the picture, you have to draw the radius. So this is rotation about the y-axis. This is r. Now from the picture, clearly r is going to x. Okay, r is going to be x. Right, and the ds. So what variable we're going to use? Because the curve is given by y equals cosine half u. So I think I still use the x variable. Otherwise, I have to solve for y, solve for x in terms of y. Right? Then become arc cosine, and much harder, much complicated. So that is a ds, right? Okay. So the area still use x variable from 0 to pi, 2 pi x, and then here 1/2 of sine half of x squared dx. So this is the integral for the surface area. Of course, we cannot evaluate. Right? We cannot evaluate. There is no formula you can use it. But you can use the computer, type the function in, and the computer gives you the estimate value. Okay, that's why here we just need to set up integral, and that's correct. Okay. 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 So now let's take a look at another example. Okay. This is a similar problem. Okay. So curve is going to be 1 minus x squared. Okay, so x is between 0 and 1. So it's very similar to the cosine curve, right? So here's difference is 1. It's also 1 here. Okay, so this is a rotation is about the x-axis. Okay, I wanted to set up two different integrals for this surface, so for the area of the surface. Okay, set up two different integrals, okay, with respect to x and y, okay, and for the area of the surface, okay. Two integrals. You have to write down two integrals. Okay, you try to write down one of them, please. Yeah. I'll give you 1 minute to think about, okay? Yeah, write down two integrals. One with respect to x variable, other one with respect to y variable. Okay, so y depends on x squared. It depends on x, and then x is going to be square root of 1 minus y. Okay, that's a relationship. And then you solve for x in terms of y, that's what you get. Okay, are you done? Good. Give me enough time. So we do it the same way, similar, right? So take a point, x and y, and then this radius. Okay, you have to draw the picture and yeah, put the 1 point on the curve with coordinate x and y. So then the area formula is always the same one, and depends how do you, what kind of variable you can use next to x or y. Okay, but it doesn't matter what variable you can use. I is always equal to y. Okay, sometimes just y, sometimes you needed to express it as a 1 minus x squared, okay, because y depends, right? Y depends on x. All right, so if you want to use x variable, that will be dy over dx squared dx. If you want to use a y variable, this is a ds, okay? So we're going to have two integrals anyway, okay? So the area is going to be from 0 to 1 to pi. If I use the x variable, I is going to be 1 minus x squared. Then I differentiate with respect to x, differentiate y with respect to x, negative 2x squared dx. So that is the integral with respect to x variable. If I use a y variable, as the interval is still from 0 to 1, and this time I is y, so I don't need to change it to x. And then what is the derivative of x with respect to y? X is going to be like this, right? No, yeah. So I have to differentiate. When I differentiate, I get the derivative, and that is going to be the derivative is going to be derivative of square root 1 minus y. So that would be 1 minus y, and I think it's 2 twice here, negative 1. Okay, it's x is square root 1 minus y. So when you differentiate, dx dy, you see, and that is going to be 1/2, and then differentiate to negative y, you get negative 1. Okay. So so you simplify, it's a 4, 1 minus y plus 1, okay, and dy. I don't think, I'm not sure we are able to evaluate integral, the second one. So definitely the integral with respect to x variable is very complicated. Yeah, okay. Second one is also complicated. So we just set up the integral. That's all we need. Okay, got it. Okay. So neither of them, we're able to evaluate integral. Okay, you can try. I don't know. Okay. So if the surface is generated by loading the curve around the x-axis, and that surface is different from the surface you generate the same curve around the y-axis, right? They're different. Okay, so you have to draw the picture. A complete solution is not just an answer. Consists of the pictures, okay, and the integrals, and then show all the steps to evaluate the integral. Right. Now those, okay, we'll have close friends and or whatever connections. When you take the quiz test, okay, you have to do it by yourself. Okay, if we find out all the steps are exactly the same, even like when you copy from somebody else, we can tell that. Okay, so we can compare. Sometimes it's easy to see, and I don't want to become a suspect. Okay, you have to show the necessary step. If you don't understand the problem, I think you just copy. Okay, so that is yeah, I got an email from the chair. I asked him to pay attention, and if necessary, I have to ask you to answer some questions online, person to person, face to face. Okay, for similar problems on the quiz on test. Okay. Right. Got it. I'll probably send an email to everybody for the midterm. All right, so the next step, next topic is about center of mass. Right? Only consider center of mass. We're not going to. This is what happened. It's from 0 to 1 to pi 1. Okay. Center of mass. Okay. If on the coordinate line, we have several points. Okay. That point has coordinates x1, x2, x, for example, n minus 1, xn. Okay, those are the points. At each point, you have mass 1, m1, m2, mn minus 1, mm. Now, the total mass, it's clear, m equals just add them together, right? This is a mathematical notation, sigma from from 1 to n, mi, okay? Add them together. It's m1, m2, all the way to mn, okay? My question is, what is the coordinate of the center? Yeah. Of the center of mass. Right? So this coordinate somewhere here, right? X bar. This is the center of mass. Okay. And yeah. So the formula for the center mass is this called the weighted sum, I from 1, and the xi mi, and divide by the total mass. Okay. That is well, it's a little bit difficult to explain if you have too many points here. Yeah, this gives you the coordinate, okay, of the center mass. Now, this is you have discrete points. Okay. Now, if you have a density function, okay, for example, you have a piece of material, okay, and it looks like that, okay. So rho over x is from A to B, okay, is a density function. Okay. Then how to find the center of mass? Yeah, yeah. Because this is, this is a solid piece, but it's not a same, right? How to find the center of mass? Okay, where's the center of mass? Okay. Now, if the density function is constant, and the middle point will be the center of mass, right? So this is x bar, right? Where's the center? The middle point. How to find the middle point? A plus b divided by 2, right? But but this is a density function. So we have to learn, we don't just memorize formula. We just need to learn how to use the calculus idea to find a formula, set up a formula. So what I'm going to do is I take a partition of the interval. Okay. So you have so many, then you have a partition, right? So you take this small piece. Okay, you take this small piece. Okay. And at this point, let me go back to here. Okay, this is the point xi minus 1 xi. Okay. So you chop off that piece. The ice piece. Ice piece is this one, right? This is the ice piece. Okay. So this is a ice piece. Okay. So the mass of this ice piece is almost equal to the density function times delta xi. So delta xi is the length of that interval. Okay. And the location of the center of this small piece is very close to xi, so we just assume it's xi. Okay. Right. So now you have a bunch of points, and then at each point you have the mass, right? Mi. So x bar should be almost equal to the total mass sigma ni from 1 to I and the xi, right? Right. You just chop off the cut this piece, yeah, this piece into many pieces. Okay. You view each piece, just small piece, as just a point, right? And all the mass accumulated, concentrated at this point xi. Right. So then the center by the similar formula above, right? We call this. Okay. And what is this total mass? Total mass is sigma ni from 1 to this. It's mi. Mi is going to be rho xi delta xi. Okay. And the one on the top, I put the xi here and rho xi delta xi. Okay. Now those are the Riemann sum of some functions. So if you let n approaches infinity, what do you get? The denominator is from a to b rho over x dx. The numerator, you just have x times rho over x dx. That's it. So you get as a formula for the center mass. Yeah, this is how do we get the formula. Okay, using this idea. Okay, using this idea, you can also find the center of mass of in the center of some area. Okay, some region. Okay, you can find the center of some region too. Okay, let's see how do we do that. Let's do it one exercise first before I talk about the two-dimension case. This is just only one dimension, okay? So if the density function is just x squared, okay? X is between 0 and 1, okay? So the material is getting, heavier and heavier, right? When x approaches, okay? This is 0, this is a 1, right? And getting heavier and heavier, right? Okay. So so the total mass m is going to be integral from 0 to 1 dx, right? So it is going to be integral of x squared, and this is 1/3 of x cubed from 0 to 1. That's just 1/3. Okay, we don't have a unit right now. All right, so can you guess where's the center of the mass? I think it should be somewhere here, okay, on the right-hand side. Yeah, the reason is more heavier than the left-hand side, right? So x bar is going to be, right? I'll have to find another integral, right? Then you find the x bar. Okay, so another integral from 0 to 1 is x rho of x dx. Okay, that's the numerator. So I get x times x squared dx, which is an integral of x cubed. Okay, then I get a quarter of x to the fourth power from 0 to 1 is quarter. All right, so that's my numerator. Then the center mass is going to be 1/4 1/3, it's a 3/4. Yes, it's on the right hand side. Okay, close to 1. Okay, so yeah, this is a picture, right? Where it is, I divided them into 4 parts, and this is in the middle of the second part. Okay, this is a center. All right, now now we're going to find. I tried to find. Okay, here's another picture. So have some region in this place, right? And this is a piece of a board, and I assume that is it's homogeneous. Okay, so the density function is constant. I just want to find the geographical center of this region. Okay, so I mark it. This is the center. For example, this is a country of some country, right? You want to figure out where the center of the country, so you put a mark there, right? Then people tourists can visit. Oh, this is the center of the country. Now, some countries, of course, does not consist of one piece. Like the United States, it's very hard to find the center of the United States because Hawaii is far away from here, right? And yeah, so it's not a good idea to find where the center of the United States. Okay, you can only say let's only consider those states. Forget this Alaska, or Hawaii. Then you can find the center. Okay. Otherwise, the center maybe goes to some place like North Dakota, someplace. So it's pretty strange. It's not a center, right? Anyway, so the question is, how do we find the center of this region? It's somewhere here, but how do you calculate, right? Yeah, how do we calculate this? Yeah, how to find the center. This time the density function is always constant. Okay, otherwise it's more complicated. Okay, constant. Yeah. Yeah, the density function is constant. We're seeing that. Okay, so how to find the center? The idea is as follows. This is x-axis, this is y-axis. So you collapse to project this whole region into one line. Okay? Then you will see that you get a density function. You know, some places are much heavier, right? So then you get a density function. Okay, so this is a density function, and you get yeah, density function, right? Okay, so you get this density function, and it depends on actually this is actually the length of this segment at the point x. The density function is the length of this. Yeah, equals the length, right, of the line segment, the vertical line segment, okay, in the region. Okay, then you can find the center on the x-axis. So x bar should be is given by this formula. Okay, if here's a, here's a b. Okay, then this will be integral of rho x dx and x rho x dx. Okay, now the question is, how do we find the y bar? This is a pretty tricky problem. Okay, because we still want to use the x variable to evaluate the integral. Okay, we don't want, now, if you can do the same way, okay, C and D, okay? Then you project everything, all evidence here. So you get another another density function. So we call it HY, okay, at point Y, and you draw a horizontal line, right? So HY is the length of the horizontal sigma, line sigma. Okay, so at point Y. So then Y bar, you can, and this is not, yeah, this is going to be HX dx, C and D is no, HY, yeah, Y and HY dy. But now you have two different variables, okay? That's okay, okay? In some problems, you don't need to use the same variables, okay? So this is an idea to take it to find the center. But I'm talking about another formula later, okay? So here's a picture, okay? Find the center of the region enclosed by enclosed by the curve y equals, let's see, y equals x squared, and x equals 1, y equals 0. So what does it mean? You have to draw the graph first. Okay? So this is a curve, x equals 1, y equals 0. So that is the region I'm talking about. Okay? Yeah, some students just cannot figure out where's the region. So I want you to find the center of that region. Okay, find the center of the region somewhere here, I guess, right? So this is the center. Okay, we assume that that region has that piece has a constant density function. Otherwise, it's probably get more complicated. All right, now, okay, how to do that? If I collapse, project this region to the x-axis, at the point x, my density function will be the length of this because it's longer than get more mass at that point. So that is going to be x squared, right? Okay, great. Okay, so now I saw, yeah, this is a point x and a y. Okay, the graph is that y equals x, but x also can be square y, right? Doesn't matter. Okay, we need that too. So so x bar is going to be integral from 0 to 1 rho of x dx and x rho of x dx. Okay, so we did the computation already. And from 0 to here's x dk, right? From 0 to 1 x times x squared dx. We already get that, so 3 over 4. Okay, we did this. So question is, how do I find the y bar? Okay, from y bar, I needed to project this region onto the y-axis. So at the point y, what is my, if I use a rho, then it's a rho y, right? Rho over y. That's okay. I use a rho. Yeah, I bet it's use a rho. It's the same, right? I did a machine. I use h. It's so fine. Okay. So I needed to measure the length of this piece. Okay, horizontal line sigma. So when y is fixed, x is going to be, and x is 1 minus x, right? Because the coordinates of that point is x and y. So, and what is x? X is square y. I have to express in terms of y. Okay. So that's it. So this is my density function, okay? So using that, I can solve the problem. So y bar is going to be integral from 0 and rho over y dy The interval is still from 0 to 1, okay? From 0 and the 1, rho y dy, okay? Let's figure it out. So 1 minus square y dy. And here, okay? I have to evaluate these two integrals. Okay. All right, so let's evaluate this integral first. The antiderivative, the square y is going to be 2 over 3 y to the 3 over 2, I think, yes. When you differentiate, I get 1/2, okay, from 0 to 1. I guess 1 minus 2 over 3 is 1/3, okay? Another one is y times square y dy. And y minus y to the 3 over 2 dy. So let's find the antiderivative. Half of y squared minus 2 over 5y to the 5 over 2. Okay, from 0 to 1. Okay, so now it's 1/2 minus 2 over 5. And that is going to be 1 over 10. Right, because 5 minus 4 is 1. Okay, 1 over 10. So my the y variable is going to be 1 over 10 divided by, I forgot what we got here. Oh, this is it's a disappeared. It's 1/3. Okay, yeah. Okay. So it's 1/3, and then it's 3 over 10. And then you have to look at the picture again. Does it make sense or not? Okay, so here's a picture. Okay, so okay, the x bar is here on this line. The y bar is below, somewhere here. Okay, 3 over 10. Here 3 over 4. I think it's pretty reasonable because much heavier lower part. And so when you get to the answer, you have to look at whether it's correct. Okay, does it make sense or not? Okay, so this will be the center. My picture is gone, so I have to bring this back. All right. So it does not save automatically. Oh, the picture's coming back. Okay, good. Okay, right. Now I go back to the region. Okay, go back to the picture again. Here's I just want to show you how to get the y bar using the integral from x to y. Okay, from x to y. So then we have to derive the formula again. Okay, so this is yeah. So this is A from B. Okay. So let's see, how do we get it? All right, I want to find the y bar. Okay, what I'm going to get to here is I use a partition. I use a partition. So I take one piece of here. Then what I'm trying to do is I consider that piece. Okay, I want to see that piece where's the center of that piece. The center of that piece will be here. It's a yi. Okay, this yi is going to be half of this. Yeah, this is yi depends on the picture, right? So if it's from here to here, this will be just at the middle point of the vertical. So if we okay, and as a density function, okay, if you collapse to here, this is a density function at the point x, right? So this is going to be the length of the still the vertical line. Okay, line is a segment. Okay, at the x. And yi, okay, let's see. So here then, so yi is going to be the center of the vertical line. Okay, at the point x. Okay, let me erase that. It's too crowded here. Okay. So I pick up a point x. I collapse this line onto x, right? So the mass at that point, yeah. So that piece is a density function. Okay. So this rho x is going to be, yeah. I'm going to use xi here. Okay, it's that because we use a yi. So rho x is going to be the length of the vertical line segment at x. Okay, so now we're ready. Okay, so this piece, if we collapsed this piece, how heavy is this piece? Right, the heavy of this piece is this is a mi. It's about rho xi delta xi, right? So that piece collapsed to here. This is my mass, mi. Okay, if you view from here, you get points here, mi. All right, so you have a bunch of points, yi around this line, and it's not necessarily in the order, okay? And this is a mass, okay? This is about rho xi delta xi. So the center of those, I have another piece here. Another piece here, maybe this is my, another point, okay? And this is if this is a xj and this is a xi, and then this will be coordinates yj, right? And then at that point, I have a mass mj, okay? And depends on that point. So you have a bunch of points on the y-axis. So the center, okay? The center y bar is going to be, okay? Is going to be add them together, right? So sigma ni, I and yi, okay? So what is mi? When mi is going to be sigma, right? Rho delta xi delta x, right? And this is going to be yi rho xi delta xi. Okay. If you take the limit, you get the you get the integral, right? So the limit as n approaches infinity, this is still going to be rho of x dx, okay? But the other one, we have to be very careful. So, so if the yi, okay, the yi, if the yi is half of the midpoint, so this depends on x, okay, at the x point y, right? So if you can express this one in terms of a function that's called the height, the midpoint of xi, okay, then, yeah, you have to find the formula for that. How does it depend on xi, okay? And then this will be h of x rho of x dx, okay? So that's the idea, okay? This is a formula. So you have to determine h of I. So if you're coming back to here as a picture, okay? And so this is a middle point, this is an x, okay? This is middle point, and rho of x is going to be the length, okay? That's called the length, right? So this is the length, and that point is a middle point on this line segment. So here, this middle point will be like an x, h of x, okay? The middle point, okay? And the length is going to be lower, is going to be the rho x is going to be the length, okay? Yeah, so on this picture, This is going to be the length. Okay, it's the length. Okay. Between A and B. Okay, if this is A, that's a B. Between A and B. Okay, so that's a picture. Okay. HX is the center. It's the y coordinate of the center between A and B. Okay. So that's it. And if the region is given by these two curves, one on the top is f of x, one at the bottom g of x, right? And it's clear that at every point x, right, rho of x is the length of this vertical line segment, so just fx minus g of x. The center is the y coordinate. H of x is the y coordinate of the center between the point, those 2 points. So h of x is going to be the center, right? So y coordinate. This is the g of x. This is f of x, right? How do you find the center? This is a center, right? This is the center, right? So just half of f of x is g of x. All right, so that's it. So that means in the future, y bar can be given by the following formula: f of x minus g of x dx, and here's the integral half of rho x. Okay, and then h of x, rho of x is f of x minus g of x dx. Okay, then so this is the formula. All right, so I'm going to go back to the problem. Go back to the problem. Okay, so y equals x squared from 1 to 0. I want to find out the y bar using that bar formula. So here's a point, center, right? All right, for this one, I have at the point x. Okay, so arbitrary point, not necessarily that particular. At point x. Okay. What is my rho of x? If you collapse to the point xx, rho x is just x squared. Okay. Now where's my hx? Hx is the center. It's the y coordinate center of this vertical line. I think which is going to be half of x squared. Okay. Half of x squared. Right? So y bar is going to be the integral from 0 to 1 x squared dx, integral from 0 to 1 half of x squared and hx, right? And then here's a rho of x, okay? Right? So this is, and then this is going to be 1/3, and that would be 1/10, okay? So the answer is 3/10. See? You get the same answer. Okay, you get the same answer. Okay, let's try another problem. Yeah, let's try another problem. Okay, I'm not going. Yeah, another problem is very similar. Still use the same picture. This time I'll consider that region. Okay. Okay. So this is x, this is y. Okay. The curve, I can say y equals still x squared. Make it simple or change the number. Okay. Maybe I just change to. I change it to 1/2 x squared. Okay. So this is going to be x2, and that is I'm not going to just use x squared. But the interval right now is 2, okay, from 0 to 2, and here's a 4, okay, yeah, 2 and 4. Okay, so find the center of this mass. Okay, I'm going to use two different formulas for y bar, but x bar is the same. Well, it depends, right? You can collapse to region to the y-axis. Okay, so the idea is very simple. You want to find this y bar, this x bar, right? Okay. Right. Let's use our formula. Okay. So at every point, right? If you want to integral over the x variable, at every point, rho of x is going to be 4 minus x squared. That is the length, right? Okay. That's the length of the line segment. Okay. Then, where's the middle point? The middle point, the y coordinate of this middle point is here. Okay. So the middle point is half of 4 plus x squared. Okay. Yeah, it's a half of 4 plus x squared. Okay. So x bar, okay, is going to be the integral from 0 to 2 rho of x dx. You write on the formula from 0 to 2 x rho of x dx. Okay. Yeah, we calculate this best. We're assuming the whole region collapsed to x-axis. So you get a density function, and you find the center of that piece, okay, on the x-axis. Okay, then you have these two integrals. Okay, let's evaluate these two integrals. So it's easy to get x bar. All right, the antiderivative, and let's do together. It's going to be 4x minus 1/3 x cubed, evaluate 2. And here's a 4x minus x cubed. So it'll be 2x squared minus 4x to the 4th power. No, 1/4, okay, then I'm going to differentiate. 4 is gone. Yeah, from 0 to 2. Okay, I get 8 minus 4, I think, because 2 to the 4th power is 16 divided by 4 is 4. And here is 8 minus 8 over 3. Yeah, this is a straight number. Okay, that's 4 and 8. I think that'll be 2/3. Okay, so what I got here is a 3 over 4. Okay. Yeah, 3 over 4. If you look at the picture, 3 over 4 is reasonable or not? X bar. 3 over 4. No, it's not unreasonable. Something's wrong, right? The center should be on the left-hand side, not the right-hand side. Oh no, 3 over 4 is the right hand because my total length is 2. Okay, 3 over 4 is on the left-hand side. Sorry for that. Yeah, because the length, it's from 0 to 2. Okay, so this is much less than 1, right? So it's here. Here's a 2. This is 1, 3, and 4 is somewhere here. Okay, so it's okay. Yeah, so it's on the left-hand side. Okay. Then if you use another same formula with respect to the x variable, that's from 0 to 2 hx rho of x dx. Okay, that's how do we calculate the y bar. Okay, just using the x variable. Okay, so that will be from 0 to 2, and from 0 to 2, the integral here is 4 minus x squared dx, and h is half of 4 plus x squared. and rho is a 4 minus x squared dx. Okay, so we just need to evaluate. The numerator because the denominator, we already get it. The denominator is going to be 16 over 3. Okay. So the numerator, let me figure out the numerator. Okay, I multiply this out. It's 16. It's a 4 squared minus x to the 4th power. Okay. So I have a 16x minus 1/5. Okay, so I get 32 minus, I think it's 32 over 5, right? 2 to the 5th is 32, the first 16, yes. Then when you do the calculation, it's just look at 32 over 2, 1 minus 1/5 is 4 over 5. Okay, so that'd be 64 over 5. Okay, so you get 64 over 5 numerator. 64 over 5. Now, after you simplify, 64 is 4 times 16. Okay, so 64 over 5 and 3 over 16. This is a 4, and that will be 12 over 25. 12 over 25 is greater than 2. I think it's reasonable, greater than 2, because greater than 2, look at the picture here, total is 4, that's a 2, so somewhere here, okay? So that will be 12 over 5, and that will be 3 over 4, so it's pretty reasonable. Yeah, you get the picture. Okay. All right, now, if you don't want to use another formula for the y bar, how do you get the y bar slightly different way? Oh, okay, I'm going to show you again. If you understand the concept, okay, this is a 4, here's 0, okay? It's a 4 and a 0, okay? This is a y equals x squared, okay? So what I'm going to do, I just want to find the center of y, y bar, right? So what I do is I collapse all the material to this y axis, okay? So the density function right now is going to be rho over y, is the length of this, okay? It is from, for fixed y, right? For the fixed y, and if this coordinates of this point is x and y, and that is just the length of this horizontal line sigma, which is x. But I want to express it in terms of y, that's square y, okay? No problem, okay? Then y bar is just the integral from 0 to 4 rho over y dy, and from 0 to 4 here, and the y rho over y, just use exactly the same type of formula, right? Yeah, because at every point, the density function is going to be square y. So along this line, where's the center with the density function square y? Because you collapse, there's a whole region collapse the y-axis. Then somewhere is more thick than the other place. The density function is just the length of this horizontal line segment, right? So then if you understand that, then right, it's easy to calculate the, if we are given the density function along the y-axis, then you know where is the center. So, right, and the bottom part is the total mass. The top part is just, the integral, right? So it gives it. Actually, the bottom part is just, the mass does not change. Doesn't matter where you collapse, which direction you collapse the whole region. So we already get it. Okay, this is actually is just 16 over. This is a 16 over 3. I don't need to waste the time to evaluate. So where's my rho over y? Rho over y is a square y. Okay, so this is the antiderivative. This is the y to the 3 over 2. So entire derivative is 2 over 5y to the 5 over 2, right? Yeah, when differentiates from 0 to 4, 16 over 3. Okay, 2 over 5 and 4 to the 5 over 2. Right, 4 to the 5 over 2 is going to be 2 to the 5, 2 to the 5th. Okay, let's figure it out. Okay, 16 is a 2 to the 4th power. So after simplifying, that's just 4 times 3, so 12 over 5. So you get the same answer, but you see the computation is much much simpler if you use this idea instead of the formula given in the book. Okay, that is the formula here. You see, you have to involve more complicated integrals. Okay, so you can find the y bar separate. The idea is very clear. Just collapse the whole region to one line, and then find the density function, okay, along this line. Then you find the center of the center of this whatever this, okay, and with the density function, okay, right. So along the line, any t, right? If you have a and have a b, if you know the density function, okay, then the math, right? I always keep saying that it's from a to b, rho over t. T could be x, could be y. Okay, it doesn't matter, right? Which, if t is x, if this is x-axis, then you use x variable. If I use this is t bar, okay? So t could be x, could be y, okay? And yeah, so this is how do we find the coordinate of the center mass with the density function, okay? And if in two-dimensional case, you want to determine the coordinates of the center of the region, you just collapse that region, okay, project that region, we should collapse, project that region onto x-axis, onto y-axis. Then you get a density function on each coordinate line. Then you calculate the center on each line, on each axis. Then you get the coordinates for the center of the region in the space. Okay. So roughly speaking, for a region in the space, you collapse it here, you get density function, then A and B, and use the density function. Okay, use the density function, you get x. Yeah. So you get x. This is the center. So center must be. This will be center of the material here, and this is the center, right? Then collapse to here, and this, right? And you get rho over y is the density function, and use that rho, you can find the center of the material. It's a projection of the whole region on the y-axis. Okay, so that's it, right? And in the book, they show you a different formula. You just use the integral with respect to x variable. Now that's a little bit more complicated, yeah, to calculate. Okay. Yeah, in the book, I think the y bar, that gives you another formula for the line. If you have to use the center of this line segment, vertical line segment, and the integrate. Right. Right. So let's continue. Let's do one more exercise. Oh no, we don't have a time. So I don't have a time. I don't have much time yet. Okay. So I said, let me list for the picture like that. And if this is arbitrary point, and this will be the center, x and h of x, right? Then let me write down this again. This is integral from a to b rho of x dx, and from a to b x rho of x dx, okay? Now you can find the y bar using the similar formula. Or you can use formula from the book, okay? And here's from a to b, and that'll be the height of the middle point on the vertical line, and this is still the same density function. Okay, either way, okay? So what is hx? That's the middle point. Yeah, this is the middle point of the line segment going through the region, okay, at the point x. Okay. And you will end up with the same result. Okay. Yeah. Okay, I stop here. Let me